Thank you for this introduction. Yeah, so partially heading off to some extensions which we have seen in the previous talks, understanding how we can make multimodals more reliable. And yeah, I'm starting here pretty soon in September. And if you're interested in this topic and looking for a postdoc or PhD positions, come on and talk to me maybe later on the coffee break. So let me start here looking at the picture what might be a blind person has taken. And the question is, what's the caffeinated drink in the fridge the system is supposed to solve? And to do that, we clearly need some form of language understanding, some form of visual recognition and reading, and probably some symbolic knowledge that Red Bull is caffeinated, so we can incorporate it in our reasoning and then answering this question. Similar, here an actual question from a visual impaired user from the WisWis data set. They ask here, what make and flavor is this coffee, please? And you notice, besides, the answer here is Timothy's Matcha Java. Besides the things I said before, like visual and language reasoning, we probably need to read text and probably copy some symbols. Or here, one more example, which happened to me last summer. What should I do after my daughter ate one of these berries? And if I want to have a system resolve this question, I need the visual recognition, I need the reasoning, but I also need or want the system to be really reliable so that any answer it gives me, I want to be sure it is right. So that's basically what I think about as reliable, that we can trust the system, what it is doing. So what is needed for this? On the one hand, I think this sort of foundational representations, both on the visual and language side and potentially other modalities. If we, for example, think about robotics, as in the previous talk, also haven't done myself anything in robotics. And here, then we need probably some explicit and implicit reasoning. For example, Red Bull is caffeinated. And last but not least, we need some self-awareness to build reliability in our models. So I'm going to talk about these three different aspects on different research we did in these areas. So let's first look at the multimodal representations, which form the foundation of this house of reliable models. So here, we looked at a model which is called Flava, and our objectives here are a strong multimodal foundation, using just public data and using and being able to do unimodal and multimodal tasks. So how does it look like? How do we learn such a model? On the one hand, we take image and text pairs. We take just images and also just text to learn this model, and then have multimodal domains and different objectives to train the system to be able to do visual recognition, language understanding, and multimodal reasoning, such as visual question answering. So some examples which I showed earlier would be multimodal tasks. Some more details about our model. We have an input image and an input text. We encode both the image and the text separately. And we have then individual losses both for the text and the image. And then we join those representations and have a multimodal encoder and have also multimodal objectives, as well as contrastive objectives between the image and the text to align them. And then we can do vision tasks by building only on the vision side. We can do NLP tasks by only building on the NLP side. And we can do multimodal tasks with a single model. And we train this all, in contrast to many prior works, on all public data sets. So it's easy to reproduce, and yeah, it's all freely available. And there's 35 tasks which we can solve in this model, or what we trained for at least. Some insights here: it's reproducible, we have diverse pre-training objectives, and we can have a joint multimodal and unimodal training in lots of different target tasks. And code, model, and data is available. So now that we've seen sort of how to build this foundation, how can we do other interesting things? And specifically, how can we solve tasks which might require explicit or implicit reasoning? And as an example here, I go back to the example about how we can make, what make and flavor is this coffee, please. We really, ideally, one idea to do that is to really read this text and copy it in the answer, to be able to generalize to any text in any image. And one question you might ask, can we do this OCR, so text recognition and image understanding, maybe separately? And for this, I have an interesting example for this. So for here, if the questions are dark chocolate cupcakes available in vegan, if you just look at the image, you actually can't answer this question. Or if I give you the text, so the OCR recognition, you also won't be able to answer this question. And even if you have them both, it will be difficult. You really need it in the image to jointly reason about it. And here is actually quite a hard image to actually read text because it's occluded. So it shows some of the challenges where OCR is actually an unsolved problem. And here the right question is no for this case. There's other examples in assisted daily living. For example, please bring me the Alexandra yogurt from the fridge, and you have to recognize yogurt container and then read Alexandra. So answering question about text, it's a challenging problem as text is omnipresent in natural human scenes. So to assist humans, we'll probably need to read, and we need to reason about those symbols in context of the image and the question. So what did we do about it? We built a model which can handle those three modalities and can reason with these OCR symbols. How did we go about it? So as I said, we want to reason about these three modalities. In addition about those, we want to represent the text in the OCR. On the one hand, using the semantic cue. So what does it mean, the actual text? But frequently, it's also important where in the image it is. And the visual clue actually found is also very important. So what does it look like? It's important sometimes to understand the importance of the text or how it relates to other text in the image, because there might be different text. For example, here you see there's a green sign, which is quite visually quite different from the speed limit sign. So there's quite a lot of differences. So last, we want to, on the one hand, predict multi-word answers from a fixed vocabulary space which we have, and also using these symbols which we copy from the OCR. So our model here is to embed all the input modalities in a common space. So we have a question word embedding, we have an object embedding of all the objects we detect in the image, and we embed all the OCR symbols with different feature representations which represent the semantics, the spatial, visual, and visual features. And then we have that in a multimodal transformer layer. And then we start predicting the answer. In this case, the answer is just, the first word is 75. And the 75 actually comes from the OCR space, so it is copied from the OCR symbol space. So we find the OCR symbol which matches, the model predicts which one it is, and then it copies the actual symbol. And the second one, miles per hour, so 75 miles per hour, speed limit, is then from the vocabulary space because it's not in the image. And then it continues generating until it eventually stops. How does this work? Well, so a baseline model from prior work performed around 27%, and then adding the multimodal transformer was very important. Just doing a single step response, so just a single word or single token response, helps with also additional OCR features. And then if you have multiple answer spaces and multiple answers, we get the best performance. And it helps to add more data from another data set as well. And there we perform similarly well. Some qualitative results to see what this model can do. For example, here, what does the light sign read on the fastest right window? The answer is but light. So here it actually takes but from the OCR, and blue and light, the blue word, from the fixed vocabulary, probably because light is a very frequent word, so it can do it from the vocabulary. And there's similar examples here. Who is the USA Today's best-selling author? How many cents per pound are the bananas? These kind of questions it can answer. So we have a multimodal transformer which can understand these three modalities. It can copy OCR symbols for use in implicit embedding and reasoning. It works well for visual question answering and captioning, and we found that lots of follow-up works use this work in their OCR visual question answering task. There's another aspect which we looked at is how do we integrate knowledge, and that's sort of what we looked at in this talk. And maybe the first question to answer is, what is knowledge? And with knowledge, I mean here symbolic knowledge, for example, that citrus is a fruit, and juice is a kind of drink, and how these can be related. And then there's also implicit knowledge, which is encoded, for example, in large language models, such as BERT or GPT. And the idea of this work is to use both of these knowledge bases to answer questions. And we applied this idea to open-ended visual question answering, like here, which liquid here comes from a citrus fruit, and the model uses both symbolic and implicit knowledge to answer such questions. And then in this case, it correctly answers orange juice. So implicit knowledge, as I mentioned, is a transformer-based multimodal BERT. So it actually already has some knowledge about images and is pre-trained. And then we use knowledge sources, in this case, diverse knowledge sources which have different relation types, which you can see here on the slide. And then we use a graph to represent these knowledge bases and knowledge triplets. And then we have some things, for example, that cake can be found at an event, a bunny is related to Easter. So these kind of relations we have all in this database. And importantly, if we now, what we extract on the left are the question symbols and the image symbols, and then we reason in this graph, which are all basically symbols, and we basically do this reasoning up to the answer space, where each set represents here an answer location. So each of the answers is basically also a symbol. So we basically have a complete reasoning in the answer space, which helps us to not lose this symbolic content. And then we combine that, the symbolic knowledge and the implicit knowledge, and the implicit knowledge is actually embedded as additional information in the symbolic graph, and they're combined with a max operation here to then predict the answer. So the key idea is here, just to reiterate, that we keep the symbolic and the implicit answer space separate to really be able to reason symbolically up to the end. And the model can then decide, based on the max operation, which features it uses. We did several appellations which show here the gray is just the implicit one, the orange is the symbolic, and the last line is sort of the full model. And also, compared to prior work, the last two lines here, we outperformed then on this open knowledge, the knowledge-based question answering task. So we have this model which can combine symbolic and implicit knowledge, and it reasons both in symbolic and in implicit spaces. So with that, I come to the last part, which is understanding how can we make models more self-aware. And I'll say a bit what I mean with this. So here, we want to increase the self-awareness of visual question answering models. Let me come to an example to explain this a bit better. Here, for example, if you think about this image, is the walk signal showing? The correct answer is, of course, no. But sometimes model get things incorrect and might say yes. But we don't want that they say something incorrect if they're not sure, but instead we want them to say, I don't know, so to abstain from answering any of those questions they're not sure or they're uncertain about. And this is what we call here a self-awareness or reliable models. And to give you an idea how difficult this is the sort of standard visual question answering task on the standard benchmark, the VQA V2 dataset. And one of the models we looked at is getting 77% of the questions correct and the others incorrect. So what we want to do is basically, we want to ideally still get all the questions correct, which the model gets correct, but then abstain on all the others. But it turns out this is very difficult. So here, if we use the model itself, so the probability or the output score of the model, it only can answer 16.1% of the questions if we want to have a very high chance of abstaining. So in this case, we look at the risk of 1%, so it can only answer 1% of the questions incorrectly. So let me tell you a bit how we try to improve that. So let me start with some problem formulation. So here, again, this example of the image and the question. And then we have a function, which is here the VQA model, which answers yes. And here we have an additional function, which we call selection function, or which is called selection function. And that tries to decide if the model should answer or not. So and if it thinks the model is unsure, it abstains or says, I don't know. And sort of this joint function is basically the selective model. And the selective prediction could be then formulated as having a threshold on the function g to either answer or abstain. And basically the most simple way of doing this, which I already talked about, is basically just taking the maximum probability of the predicted answer. For example, here if the predicted answer is yes, we take that probability and threshold this probability to decide if it should be yes or no. And basically this doesn't require any additional training, it requires fine-tuning this threshold only. And what we now do is basically train a multimodal selector. And a multimodal selector means that we take features from this function f and train a small neural network which predicts if the model will be right or not on held out data. And this then allows us basically to jointly predict the answer and if it should abstain or not. And there's been prior work in this back into sort of OCR recognition. They had sort of a reject option, and there's been also more recently work which does it on single modalities. And there's also been some work on out-of-distribution data in text-based question answering. But we found that actually for the multimodal case, it seems to be especially hard, this task, compared to some of the results we have seen in prior work. So here we look at the visual question answering task, and we have a data set A, sort of the training set A, which we use to train the model F, and then a data set B, or train B, where we train the selection function. And here we evaluated multiple models, but here I'll focus on the model the best model which we evaluated most recently, which is the OFA model. So here, again, the slide with the results. We have this standard VQA setting, and on the right, the best possible. And if you use MaxProp, then, as I said, we get about 16%. But if you use our selector model, we get roughly double the performance here. But we still see that there's like a huge, basically, gap of performance. So this is sort of a very challenging task, which we also plan to work on in future. Some examples of this. Just maybe to explain why Y is basically the ground truth answer. But there's, in this data set, there's 10 ground truth answers, so we have here, we listed them all here in this example. The first question is this bird looking at the camera? the model incorrectly predicts yes, but the selector basically abstains. And in a second example, what is he doing? The model actually correctly gets skateboarding, but the maxboard model decides to abstain. So we have seen for reliable visual question answering that VQA models have really poor performance when they have to be reliable, so having a low risk of getting things incorrect. A selector can improve performance significantly, but there's still a big gap to an optimal case. And the code is available on this web page here. So now, a sort of extension to this work recently looked at how is this in an out-of-distribution setting. And with out-of-distribution, I mean things which are not directly in the training distribution. And this really is a bit dataset dependent, but there will be always something out of distribution, either because you haven't seen it, because it's a new concept in the world, or you have just a different domain where it's slightly different. And we found models really struggle with that. So let's look at the example here. If we just have 10% of the data out of this distribution in the test scenario and the 90% still in domain, the performance from this 16%, which I mentioned earlier, drops further to just 1.3% of questions being able to answer it. But with the selector, we're still able to answer about 23.3% of the questions. So that's quite encouraging. We can even do slightly better by additionally to having this selector trained. If you remember, I stressed that we actually need two data sets. We need the training set A to train the VQA model, and we need the data set B to train the selector. So what we do is here, we try to split the data in a way that we can train each multiple VQA models on different subsets of the data and label the model on the remaining data. For example, we can train it just on D1 and D2 and then evaluate it in D3 to label it there and train the selector with those labels. And this in the end actually allows us to train the VQA model with the full training set, and we're also able to train the selector on the full training set. And this then can give like a further slight improvement reaching up to 25% of questions answered. Maybe interesting is that different models behave quite differently on out of distribution. So we found, for example, that here the model which I've been talking of so far, which is the blue line, this is a slightly different evaluation metric. This allows 5% of error, so a risk of 5%. But if you look at the very left and the blue line, that's basically what we had, the model we had so far. But then this model drops like dramatically as soon as we increase the percentage of OOD data, and that's true actually for all the models. And maybe I skip this one, but then here, if the model also has to generalize the threshold of when to abstain or not, then the best model, which is the blue line, becomes the worst model very quickly once it gets to more OOD data. Also, one has to be said, there's sort of a zero line, so things which are below zero, they're basically not really useful anymore. So we see with higher OOD percentages, models become really not operable or useful for this task. So we found that existing VQA models are overconfident in out of distribution, with just 10% out of distribution to achieve 1% risk of error. Out of the box confidence can only answer less than 5% of the questions. Our performance can benefit from learn multimodal selection function performance, and selective VQA with OOD is still a very challenging setting. So the last thing I want to talk about how we extended this to long sequences of answers. So, or long sequences of text. again, in a multimodal setting, for example, here, if we have this picture, a bluebird is next to a red berry, and we have vision and language models which try to understand it, for example, image caption, consistency, how well are those related. We find that many models are good to in generally do it well, but they have difficulties with details. For example, here a red bird is sitting next to a blue berry, just swapping around these adjectives. They have it very challenging to do that. So idea is basically to look at individual words in the context of the rest of the sentence, rather than judging the entire sentence at once to decide if things are correct. So here, for example, the task could be a bluebird is next to a red berry. Is this correct or not? And what we do is basically, as I said, to basically look at all these individual words. And we look at two variants here. On the one hand, we look at algebraic conferences, which basically means we look at the output vocabulary distribution, and we use also, in the second stage, we use a learned confidence, similar to what we have previously done. So let's first look at the algebraic confidences, how that just works already quite well compared to prior work. Here we're looking at Winogrand, which has these fine-grained details of captions versus images. And we'll see that throughout these different, here we see always the light purple and the dark purple is basically the improvement we get by looking at the same model, but adding sort of single token correctness estimates, and the gray bars are prior work. We can also apply this to captioning, so which means generating a caption. And we find that the standard model gets around 2.7% of captions where it hallucinates, so generates wrong objects. And our models get significantly lower hallucination rates on this task. Some examples here. For example, here, when we generate a caption, so a text describing this image, the baseline would say a blender with chopped apples in it on the table. And our model, which is trained to do this task, a blender filled with fruit on a table. There are several more examples where it's sort of in a similar case. Again, the state-of-the-art models can struggle with understanding this caption correctness, and our sort of simple model can significantly help to improve this performance, but there's still quite a lot of work to do to get this right in all the cases. So with this, I'd like to shortly look at future work. We looked at all these different aspects, but one aspect which I didn't talk about and which I'm excited to explore in future is how can we make that person specific? Right now, for example, I assumed that we have the same thresholds for all the questions and all the tasks, but maybe you really need different thresholds for different tasks, and different people have different strengths and weaknesses. Another is out of distribution, which I just mentioned, where we, I think, just have scratched the surface to handle, and I think it's a wide challenge to handle this task. And then last, continual learning, which has also been mentioned previously, to sort of continue to adapt to new scenarios, to new environments, new concepts which appear over time. And with this, I'd like to conclude this talk. So we have seen that we have built a foundational models with public data and which is able to do unimodal and multimodal tasks. We've talked about explicit and implicit reasoning and how to combine them, and that's sort of the important aspect. And we looked at how to make models reliable or self-aware by using a selector. But overall, it's a big challenge, especially if you have any out-of-distribution data in our scenario. And there's lots of diverse challenges ahead in out-of-domain and continual learning. So yeah, if you're interested and want to work on this, just reach out to me. There's a broad set of topics I'm interested to work on here at TU Darmstadt. So excited to work with you, either in a collaboration or as part of a PhD or postdoc. And with this, I'd like to thank all my collaborators of the different works I've shown today. And I'm happy to answer your questions. I'll try to reliably answer you, but sometimes I might abstain. Thank you.
Thanks a lot. So again, you open up for questions from the audience. I see one over there in the middle, and also one there.
Thanks for the very interesting talk. I have a couple of questions. One was you mentioned that when you merge implicit and symbolic conflicts, you try to keep them separate. How do you handle, for example, blatant conflicts? So, for example, if the symbolic information or symbolic reasoning says that it's an orange, and your transformer has learned that it's, for example, a mango or something.
Yeah, I just pull up the slide that people who might not remember it. So, yeah, they are combined in a max operation. So I guess what I meant to, maybe the more precise formulation is, they're not combined in an embedding space. They're combined with a maximum operation. So basically, overall, there's sort of a confidence, and whatever model is basically more confidence overall, and this answer is packed. We also try to do different combinations. You could, for example, average those, but that tends to be not as good.
I have another question, but I can wait for other people.
I think there was, maybe we take another question and we go back.
Yeah, thank you for your interesting talk. That's the right slide, because you mentioned to incorporate symbolic knowledge, and I wonder, how did you get this knowledge? Did you generate it manually, or did you use some kind of learning extraction algorithm?
Yeah, that's a good question. In general, you could use any knowledge base you have, and in this case, we use knowledge bases which match sort of the ideas of our questions. So these are existing public knowledge bases. We haven't built them ourselves. Some are sort of more manually constructed, and some are automatically or semi-automatically constructed. For example, I think there's like some which are, I think DBpedia is basically based on Wikipedia. So it's basically a concept database which is constructed based on Wikipedia articles, which are themselves manual, but then I think the actual database is then automatically constructed. I don't know the exact details, unfortunately.
Thank you.
I think there was one question, maybe in the same row.
Right. Yeah, thanks again for the talk. So my question is, when we look at diffusion models, for example, the Imagine model could greatly improve because it was based on a language model which was trained on more diverse data than only small captions. So when you train on, very often these multimodal models, they have image-text pairs, and the text is always very small captions. And we often say an image is worth 1,000 words, and if you have only small captions, it's probably difficult to extract the essence. So when you try to incorporate more knowledge, would it be also sensible, like in the Imagine model, to take more of the textual model, to incorporate it more?
I'm not sure I get the question. To use more text data, like longer text data?
Yeah, exactly. Like, yeah.
Yeah, I think in general that could. I mean, that sort of would be then more sort of on the implicit side. You could train with larger data. In fact, this is based on a BERT model, which was trained on longer data, not just captions. So I'm not sure if that fully answers your question.
Yeah. I was simply wondering why why, for example, in the fusion models, it could help improve so much, but here it couldn't. Whether you have a take on that.
So I don't think my claim would be that it can't help here to have longer captions. I'm not 100% sure why it helps there. I think it's just sort of the more data you have, and probably because the more diverse data, and that can help with handling more. Because if you allow more long text, you can take more diverse text and more amount of text. That probably is the reason why it might work better. But I also don't know. That's my hypothesis. I don't have studied that, so it's difficult for me to say.
Thanks.
Should we go back there?
So in your selectors, do you think it adds some advantage if we explicitly encode some priorities? For example, it's riskier to misclassify a red than an orange or green.
Yeah, no, I agreed. I mean, that's sort of what I managed with, sort of making it maybe person-specific or task-specific, where you maybe want different risk levels for different tasks. Yeah, so that makes a lot of sense. I think that's not so easy. I mean, it's easier said than done, because estimating the risk level is a task probably in itself, and we don't have any data right now to know what would be what you should. Maybe different people have also different preferences, so it becomes really tricky. Of course, you could sort of simulate it, but we haven't done that. But I think it's probably an interesting task. But probably, I think the data is just not there also to do that in a realistic scenario. I don't know.
There are some more questions down here. We still have time, so.
So thank you very much for the talk. It was very interesting. There have been some new papers on, well, decoders specifically, but transformer models where they make the model first go through its reasoning and kind of talk about the task, and then conclude with some specific answer. Do you think that would be a way of increasing reliability? For example, having the classifier decide whether that reasoning text output makes sense according to common sense, instead of classifying on the embeddings?
Yeah, I think that could be a possibility. I'm not 100% sure how well it will work in sort of this multimodal setting. I've seen it sort of on text-only models, that they can do it, especially if they're especially large, that increases their modality. I haven't seen this work, so it would be interesting to potentially explore. I think that's next question.
So one more question over here.
Okay, thank you very much for your talk. So you showed examples for visual question answering, which are mostly classification tasks, like what category is this, or yes or no. And I'm wondering, what about regression tasks? For example, what number or how many people is this picture showing, or what's the distance between those two objects or something? Did you already or also work with that, and how does abstention work here, for example?
Yeah, I think that's a very good question. We haven't explored that. Also, I have to say, actually, our model does regression. So it does regression to so that's very data set specific, so that's why I didn't mention it. But I thought there's like 10 different answers, so you can be a bit more correct and a bit less correct. So the data set has sort of a score how correct one answer is. And we basically regress to this number to get better performance. If you don't do it, you get slightly worse performance. And we basically use still the same technique. So in general, it should be still applicable to regression. Of course, then it's sort of, you don't have a binary correctness anymore. So right here, we look sort of more or less binary correctness. Also, basically what we're saying is like, as long as it's somewhat correct, we treat it as correct. And if it's completely incorrect, if it's sort of the score is 0, then we treat it as incorrect. But the examples you mentioned are a bit different in the sense that you could be a bit off, And then you would have to probably either work more with probabilities, which would be interesting to look sort of what MTS talked about, like maybe more Bayesian models, or you have to define a threshold where you can live with, and above this threshold, maybe you can't live with.
Good. Then thanks a lot for the interesting discussion and the talk, and let's thank the speaker again.
Thank you.